Good afternoon, my dear students. In the last class and before last class, whenever your fluid mechanics started, we'll discuss about all basics like definitions, fluid mechanics, introduction, and all we'll discuss. And we solved viscosity problems. Further, we will discuss Pascal law and the problems related to Pascal law. Then we measured pressure measurement with the help of U-tube manometer and differential U-tube manometer. We'll discuss. In coming further chapters, we'll discuss about fluid kinematics, which is a part of your dynamic behavior. Your dynamic behavior is classified generally into two categories. One is your kinematics and another one is kinetics. And in the fluid kinematics, we'll discuss about velocity, acceleration, and movement of fluid. That means flow of fluid, that is displacement, without considering the force effect. That means what is the cause we will neglect, and we'll study about the effect. Okay. Further, we'll see. For that, first I have chapter wise content. Still, it is a big chapter. So, in coming 3-4 lessons, sorry, 3-4 classes, we will finish this. First, we will discuss about fluid flow. Then, fluid flow methods. There are two methods here that we will discuss. And laws, generally how many laws are there related to fluid mechanics, that all we'll discuss. Then about flow, continuity equation we'll discuss. Then Euler equation will derive. Based on the Euler equation, Bernoulli equation we will get, and linear momentum equation, angular momentum equation, energy equation we'll discuss. First topic of today's lesson is your fluid flows. Coming to the fluid flows, why we need to study fluid flows? That is first important general question everyone will get, because the fluid behavior is not same in all instances. I'll tell you a simple example. I have a bucket of water which is stationary, no force is applied. Now I have a spoon of surf which is poured inside the water, and I applied a small force, then swirled it. Then obviously water will swirl about one axis, about one point it will swirl. So the behavior of fluid here and the behavior of fluid here is different, completely different. There is no relation. Similarly, you are constructing a dam, okay, without considering the effect of fluid flow. Then how it will be, I'll tell you. For that, I have taken a dam, okay, and your dam is like this. Some water is inside the dam, okay. You have water is stationary first. For instance, water is stationary. So I have not considered any type of flows. Just simply I constructed a dam for constant flow or the saving of water. So after some days, what will happen? This dam is filled with water. Like then you opened a small amount of gate. So the flow of water is trying to escape from this small amount of gate. Okay. The behavior of fluid particles, if you observe, is different. When it is stationary, the behavior of fluid particles is different. When it is moving, the behavior of fluid particles is completely different. Okay, that are energized. When the fluid particles are energized, which has force, which has momentum, you are not able to control that fluid particles. So even you open one gate, the part of this portion may damage. Okay, to avoid that all losses, you have to estimate what is the force acting under dynamic behavior also. For that, this chapter is very interesting and useful. Okay, first we'll discuss about uniform flow. First flow is uniform flow. Comment the uniform flow. Uniform flow means, example, I have a flow field. For a length, I have a canal. Inside the canal, some fluid is flowing. Okay. So first what I did, here two flows are there. One is uniform flow, another one is steady flow. Steady is different from the uniform. Okay, that point you can keep in mind. I'll explain both at a time. Coming to the uniform flow, I have selected a point. Your total length is L. L length of fluid you have. You have selected a point X. Okay, about this X point, if your velocity and pressure is not changing, that means constant. So how I'll write in mathematically, the change is represented partial differentiation, dou, V. Why I'm taking V? Velocity, dou V with reference to dou X. Why X? Because about one point I'm considering, that is X, the change of velocity with reference to X is equals to 0. There is no change. Then we call that flow as uniform flow. If it is not equals to 0, then we call it as non-uniform flow. Okay, I'll repeat again. Uniform flow is simple as it is. The velocity, pressure, acceleration, these are all conditions with reference to one point, X is not varying. Then we call it as a uniform flow. If these are varying about a point, then we call it as non-uniform flow. Okay, that means the change of velocity with reference to X is equals to 0, then we call it as a uniform flow. If it is not equals to 0, then we call it as non-uniform flow. Now we'll go further. Steady flow. Now why steady flow is coming to picture is, same flow I measured for t seconds. Now I'm not considering X. With reference to t, I'm measuring now. So if you take with reference to t, so how can I write equation now? You can check the velocity dou v with reference to what? Time is equals to 0. There is no change with reference to time. That means I considered that flow for 1 hour. I checked it for 1 hour. But there is no change in the velocity inside the flow. There is no change in the pressure. There is no change in the acceleration. That means the change of velocity change with reference to time is equals to 0. Similarly, the change of pressure with reference to time is equals to 0. The change of acceleration with reference to time is equals to 0. Then we call that flow as steady flow. If your pressure, velocity, acceleration, such components are changing with reference to time, that means change, partial differentiation is not equals to 0, then we call that flow as unsteady flow. If the conditions at one point vary as time passes, that means based on your time, if your conditions are varying, then we call it as unsteady flow. Now I hope you understood what is uniform flow and non-uniform flow, steady flow and unsteady flow. Okay, simple. In what is the outcome from here? Uniform flow is with reference to a space, with reference to one point. At the same time, steady flow with reference to time. Okay, now we'll go further. Same thing, whatever we discussed there, same thing is mentioned. I'll share this PPT for your benefit only. I added that also. Now, some fluid flows. Now you can mix both, because we studied steady flow separately, unsteady flow separately, uniform and non-uniform separately. So there are some fluid with reference to time, it is changing. Okay, sorry. If you take steady non-uniform flow, that means with reference to time it is constant, but with reference to space it is changing. Okay. Now unsteady with reference to time it is changing, but with reference to space it is constant. Okay. Unsteady non-uniform, that means it is either with reference to time not constant, with reference to space also, point also not constant. Okay. Now what will the equations for these all? You can see here. Now how can I write? Dou P by this steady. That means with reference to time it is constant. Dou p by dou t is equals to 0. At the same time, dou p with reference to dou x is not equals to 0. Okay. For this, how can we write? Unsteady. That means dou p by dou t is not equals to 0 because there is a variable, it's changing. But it is uniform. The dou p by dou x is equals to 0. If you write for last equation, that is dou p by dou t is not equals to 0 because it is changing with reference to time. Similarly, it is changing with reference to space also, not equals to 0. Okay, I hope you understood this. That's why I'm going further. That is one dimensional, two dimensional, three dimensional flow. Okay, if a fluid flow is with reference example, I am writing v is equals to x square plus y square z square. If your fluid flow is following this equation, then we can simply call it as three-dimensional flow, a spatial flow. Okay, if it is varying like v is equals to 2x plus 3x, then we call one-dimensional flow. If your velocity is varying 3x plus 2y in two directions, then we call it two-dimensional flow, as simple as it is. Okay, same thing is mentioned. If you, in general, a three-dimensional equation is written, there is a change in velocity u direction, v direction, w direction. What is u direction? Along x, u direction, along y, v direction, along z, w direction. That means that equation, whatever the equation of that flow, if you are writing, if you are mathematically deriving that equation, or you are mathematically modeling that flow, that comes out to be x, y, z equation, then we call it as a three-dimensional flow. Okay, as defined above, flow will be uniform if the components are independent of spatial position, will be steady if the velocity components are independent of time. Okay, now we'll go further. So with this also you'll get same idea. See here, classification of flow. In this example, what he did, a pipe you have, okay, here somewhere some vent is there. So here first section he considered, and here second section he considered. So now this problem is one-dimensional problem or two-dimensional problem, we have to consider. We have to check. If your fluid flow is moving in this direction, there is no cost, there is no problem. Here also you are just compressed, your velocity and pressure is changing. But if you are writing an equation, it is moving in one direction. So it is one-dimensional flow. Okay. If I have a small hole here, then fluid is trying to escape from this hole, then it might be two-dimensional, it might be three-dimensional. For that you have to mathematically model it. So simply you can write one-dimensional flow as, if your fluid equation after mathematical modeling showing only one direction, either x or y or z, that means the equation may be like 3y plus 3z, sorry, 3y square, or it may be like this 3z plus 3z square. That all called one-dimensional flows. If your equation containing velocity along x, along y, along z, then we call it as three-dimensional flow. If your velocity having u, v, then we call it as two-dimensional flow. Not exactly uv, it may be vw, or it may be uw. Any two types of velocities, two directional velocities has to be involved in your mathematical modeling, then we call it as a two-dimensional flow. We go further, viscous flow and non-viscous flow. Coming to the viscous flow, in viscous flow, if you are with the help of viscosity, your fluid behavior is changing. That means your flow is affecting. Okay, that is inviscid flow. Inviscid flow is viscous effect is not affecting. That means it is not affecting, then we call it is inviscid flow. But in viscid flow, that means viscous flow, it will affect based on your viscosity. It will affect. Okay, as simple as it is. From the viscosity definition, also we'll get same thing, same outcome, right? So about this, I'll come back later. In after some time, I'll come back. About this also after some time, I'll come back. And there are two more flows. Actually, total 6 types. I'll discuss at the end while writing a total summary of this. Compressible flow and incompressible flow. So I have a bucket of water. So I have piston arrangement here. If I'm applying force on that, is it will compress. I have a balloon. Okay, a rated tube. So I'm sending air inside. When you are sending air inside, it will take more amount of air. But it will take, example, this bucket of 10 liters. It will take maximum of 10 liters only. But in case of your tire may take more also. It may take 20, like filled only, 25, same filled looking filled only. So it is very clear. In the fluids, there are two types based on your compression, your density change. Okay, that is compressible fluid and incompressible fluid. Okay, first, the fluids are compressible. All fluids are compressible. Even water also compressible, but we will consider water as a standard fluid. That's why at 4 degrees centigrade only, water is considered as a standard fluid. So why it is saying compressible? Because there is a small change. First, we'll define what is the compressibility. If there is a change in the density, there is a change in the density, then we call it as a compressible fluid. If there is no change in the density, irrespective of force applied, then we call it as an incompressible fluid. Okay. Under steady conditions and provided that the change in the pressure is small, it is usually possible to simplify analysis of flow by assuming incompressible and constant density. So, for our analysis, we are considering all fluids are incompressible in nature and steady in nature, best in nature. Then only you can derive the Bernoulli's equation or any other equations. The ideal conditions we will consider. So, what he's saying, what is the outcome of this? Simply, if your density is constant throughout, then we call it as which type of flow? Incompressible flow. If there is no change in the density, change of density is zero, then we call it as a incompressible flow. But when you are applying the pressure, if your density is changing, that means your density is not constant. Change of density is not constant, then we call it as a compressible fluid. Okay, gases, most of the gases, not most of the gases, all gases are compressible in nature, easily compressed. Okay, that's why in boundary layer theory we'll discuss about this in detail. Okay, here what is the outcome is only one small outcome we have, that is incompressible flow and compressible flow. Coming to the incompressible flow, if your change of density is equals to 0, then we call it as incompressible flow. Your density is changing with reference to pressure, with reference to temperature, then we call it as compressible fluid. We go for the laminar and turbulent. It is one of the important classification. Actually, it is, we have an experiment on this also. In lab, we will do it. A jet, a dye is there, which is some color liquid. Okay, this color liquid has some entrance here. You have fully filled color liquid, some entrance here. From this entrance, you are sending the water. Later, this is the water, and it is a color liquid. So when you are sending this water, if the stream, the outstream, this is out, is looking like this, then we call it the laminar. If it is looking like this transition, it is looking like this turbulent. So by seeing, we can't say like that. For that, we have experiment. We'll discuss about that why in the lab also. But I'll discuss some more detail about this. If you have fluid particles, I'm discussing about laminar first, are parallel to each other. Example, in this, if you draw exaggeratively outside, the fluid particles are parallel to each other. The fluid flows. It has n number of layers. The all layers are parallel to each other. We call it as a laminar flow. Simple as it is. If the fluid particles are not parallel to each other, very zigzag, random in nature, then we call it as turbulent. The phase transition is a phase which is changing from laminar to turbulent. If your fluid is changing from laminar to turbulent, the intermediate phase is called transition. Okay, as it is. But you may ask a question, sir, sometimes this flow is looking like a laminar, but if we deeply observe or if we closely observe, it is looking like a turbulent, a transition. If you take a small portion of the transition flow, it is looking like a turbulent. If you take a small portion of a transition, it is looking like a turbulent. Sorry, a turbulent. If you take a small portion of a turbulent, it is looking like a transition. How can we decide? For that, the person named as Reynolds, he, he derived the equation or a number, a dimensionless number that is called Reynolds number. So by using Reynolds number in a closed conduit flow, we will define laminar, turbulent and transition flow. What is Reynolds number? It is simply the ratio of inertia force to viscous force. So we'll calculate inertia force and viscous force of that particular fluid. Okay, what is inertia force? Rho Vd. Okay, because d diameter, v velocity, rho density, and mu is viscous force, viscosity. Okay, so if we did the ratio of this is Reynolds number. Based on the Reynolds number of, there is a experiment called Reynolds experiment. Based on that experiment only, we'll decide what type of flow it is. If you are in a closed conduit, that means in a pipe, if your fluid Reynolds number is less than 2000, then we call it as laminar flow. Between 2000 to 2800 or 4000, some books it is written 2800 and 4000, both are in practice. Most of the books is written 2800 standard books. Then we call it as a transition flow. This is also, if it is 2800, then we call it as turbulent flow. Once again, I'll repeat, coming to the laminar flow, if your fluid flows are parallel to each other, then we call it as a laminar flow. Transition flow is phase changing from laminar to turbulent. Turbulent is simply a zigzag flow where your fluid particles are not parallel to each other. Okay. Now, one more fluid flow we have, that is rotational and irrotational flow. Coming to rotational and irrotational flow, a basic understanding, a simple understanding, a simple example I'll tell you. You have a sink, a wash basin. Okay. You have a hole here. Let I have another wash basin where hole is at center. Different types of wash basins we have in the market. So let this wash basin is filled with water. This wash basin is filled with water. Some cap is kept here. You remove the cap. Then what will happen? Water will flow like this. You observe here, water will flow like this. Okay. Now, for this case, where will the mass center? This total liquid, somewhere mass center will be at center. Here also the mass center is center, but the flow, the whirling flow, is not going about this point. About this point, it is going about your hole. Catching my point? Here, the hole is at mass center. That's why fluid is going about the mass center. Okay, that's why there are two types of fluids. If it is a rotational fluid, the fluid particles has to go about its own axis. Okay, about its own mass center, it has to rotate and it has to go about its own axis and about its mass center. If it is not going with reference to its mass center, then we call it as a rotational flow, as simple as it is. Okay, based on this only we have two more flows, stream flow, streak flow, that we will discuss in coming chapters, coming slides. So I'll tell you total summary. First, steady flow. So when steady flow is there, unsteady flow also there. So I hope you understood with a reference to time it is dealing. Change of time, change of pressure with reference to time is not there. It is constant, zero. Then we call steady. It is not zero, then unsteady. Next, uniform flow. And another flow is there, non-uniform flow. First, I'll write this. The change of pressure with reference to point, any point is equals to zero. But if you write unsteady flow or ununiform flow or inuniform flow, non-uniform flow, any term you can write, generally non-uniform flow we'll write. Coming to the non-uniform flow, the change of pressure with reference to space is not equals to zero. In the unsteady, it is not equals to zero. In the steady, it is equals to zero. Next, one-dimensional flow, two-dimensional flow, three-dimensional flow. It's very clear. If your fluid model is varying with reference to u, with reference to 2, with reference to 3 velocities, UVW, either UV, any two U indicates the velocity profile along X, the V indicates the velocity profile along Y, W indicates the velocity profile along Z. Now next flow, rotational and irrotational. Just now we discussed with reference to mass center, it has to rotate. Without mass center, somewhere about your flow, it has to rotate. Next flow, laminar flow and turbulent flow we discussed. Laminar flow means your fluid particles must be parallel to each other. And turbulent is simply a zigzag flow. The phase which is coming from laminar to turbulent is called transition flow. The phase which is coming from laminar to turbulent is the transition flow. The phase which is coming from laminar to turbulent is transition. Any other flows we discussed? Let me check once. One more flow is missing actually. Yes, inviscid or viscid flow. So with reference to inviscid and viscous flow. Viscous flow means there is no effect of viscosity. Okay, and inviscid flow has a viscosity. Thank you one and all. With this, I'm closing today's lesson.